In this video, we're going to introduce the limit concept. The limit concept is central throughout calculus, and it helps us to develop two primary branches of calculus, namely the derivative and the integral. So it's really important to understand and appreciate limits. Let's begin by exploring the behavior of the following function. F of x equals x squared minus 4 over x minus 2. We want to explore that behavior near the value of x being 2. And the reason this is of interest, you might notice that if we tried to evaluate f at 2, then we would get the numerator equal to 0 and the denominator equal to 0, and that's a problem. That becomes undefined. The numerator can equal 0, but the denominator can't be 0, so that's why this is a point of interest. So we're going to explore the behavior of f using two different representations. One, we want to look at the graph. So first we're going to look at the graph of f, and then we're going to look at tables of values, or a table for f. So let's take a look first at the graph. Now you might prefer looking at the table first and then the graph, and that's fine. Your teacher may prefer a different order, but I'll start with the graph. So for part A, looking at the behavior of f using a graph, first we want to notice that x is not equal to 2. We can't let x equal 2, and that's because if we do let x equal 2, the denominator goes to 0, and that becomes a problem. So if we consider x not equal to 2, we can actually graph this function. So let's do a little simplifying first. You might have noticed that the numerator is the difference of two squares. And if x is not equal to 2, then we're allowed to factor the numerator, x minus 2x plus 2, over the denominator x minus 2. And then we can actually cancel or simplify. We can scratch these. X minus 2 over x minus 2. Since x is not equal to 2, we can actually simplify this a bit. Divide out the x minus 2's. And so this is what our simplified version of the function is. So when x is not equal to 2, anywhere else but 2, the function looks like this line. And so that's going to be our graph. So let's draw an xy axis. There's my y, my x-axis, 1, 2, 3, 4, 1, 2, 3, 4, there's my y, there's my x. And so whenever x is not 2, it looks like the graph of the line y equals x plus 2. So this is f of x equals x plus 2. Now, we have this little issue that at x equals 2, it's undefined. So let's knock a little hole in the graph right there. And usually we represent that with an open circle to say the graph is not defined right at this spot. But everywhere else it's okay. It follows this line, this linear pattern. This is at -2. Okay, so this is our graph of f of x. Okay, and now we can use the graph to give us a little insight for our table of values. For our table, we're going to look at x values and the f of x values, and we want to look for x values that are close to 2, getting closer and closer to 2, but not actually equaling 2. Now there's two ways we can do this. We can approach 2 from the left-hand side, something like 1.9, 1.99, 1.999, and so on. We can keep going on as long as we like, but this is plenty. And then on the other side, if we approach 2 from the right-hand side, just to the right of 2, we could say 2.1, 2.01, 2.001, and so on. The idea is we're trying to show a pattern of y values, or f of x values, as the x values get closer and closer to 2 from one side and the other. Let's take a look at what these values look like. Here's our equation for f of x simplified whenever x is not 2. Remember, whenever x is not 2, this is the equation we can use for f of x. So x plus 2, or 1.9 plus 2, is 3.9. This becomes 3.99. 3.999 and 3.9999. You might notice that these values appear to approach 4 as the x values approach 2. And that is consistent with our graph that as we approach 2 from the left, the y values along the graph, the y values are our limiting values, they approach what appears to be 4. So the x values approaching 2 from the left give us y values along the graph that seem to be pointing at 4. And if we look at the x values approaching 2 from the right-hand side, so this is the 2.1, 2.11, 2.1, 2.01, and so forth. 2.1 plus 2 is 4.1. This is 4.01, 4.001, 4.001. You're getting, I think, the gist of this pattern. Here we're approaching 4 as the x values approach 2, and that is consistent with the graph that as x approaches 2, the y values are approaching 4. So this missing value, the y value, the limiting values on y value, is 4. And mathematically, we can write this as follows. So mathematically, we write the limit, LIM for limit, as x approaches 2 of x squared minus 4 over x minus 2 equals 4. That's how we can write the limit expression mathematically, which is the same thing we've written here graphically or using a table. So one little summary that I want to put together at the end, and this is sort of like an informal description of what it means for a limit. In general, if f of x, the y values, get closer and closer to some number, L, as x approaches some number c, so in our example, L was 4 and c was 2, from either side of c, but not necessarily equaling c. It can be, but in this case it wasn't. Then we say that the limit of f of x as x approaches c is equal to L. And we write this general limit as limit as x approaches c of f of x equals L. And so the only thing I wanted to add, and this sometimes confuses my students, I wanted to make sure that you realized L was representing y values. And I'll say y values because sometimes you don't have a y, sometimes you might have another variable. But these are the dependent variables, the y values. And this, the c values, are the x values. But the answers you're looking for, the limiting answers, are actually y values. I hope this gives you just a nice general overview to the limit concept. And in some later examples, we'll look at more applications of the limit.